Hi, in this video I'll be discussing preliminary well log interpretation, which should be quite useful for you at the well site. Now, prior to interpreting your OpenOL well logs, you would need to have at your disposal all relevant daily drilling reports, also surveys from the last well, the last casing depth, and mud data. Usually you would require the mud, the resistivity of the mud, and the resistivity of the mud filtrate at formation temperature. Also, the most recent mud log information should be at your disposal, cutting descriptions, anything as regards gas readings across the zones drilled, rate of penetration, and importantly, core data if available. And logs and interpretations from nearby wells and also regional interpretations usually come in handy, where field-wide values of the exponents M and N, and then water resistivity, and also bulk density information with also contacts are available. And then you would need a copy of the contractor's chart book, which would also show its utility in this video. This will allow for compilation of all information about lithology, especially expected rock type and mineral composition, presence and type of shale, spore types, and some other information. So prior to reaching the total depth, whether you're going to run the logs on wireline or whether it's done while drilling, it's to be helpful to have this on hand. The general goal of interpretation is the determination of the lithological profile and detection of potential reservoir zones at the exact depth, shale content and type of shale, porosity, and in some cases mineral composition, fluid saturations, and if you have NMR, that's nuclear magnetic resonance data, also permeability. So interpretation delivers solution in two steps. Usually there's the quick look interpretation, which is more qualitative. Of course, even though some quantitative evaluation can be done at the well site too. And then there's detailed quantitative analysis, which is usually carried out in town. So as you've seen, or as I've alluded to in the earlier slides, you don't interpret the log in isolation. And that's why log interpretation requires the synthesis of logging tool physics, geological knowledge, auxiliary data, everything available on the subsurface comes to bear. So knowledge of the characteristics, log responses, empirical and model-derived equations for quantitative interpretation, and then the interpretation of all integration of available data, and the skill of the interpretation of the interpreter comes to bear. So the first step is quality control of the logs available. So before I go into the interpretation process, I'll just highlight some important things which the interpreter, whether the petrophysicist or the field engineer, should take into cognizance. So you have to check the logger's total depth, the last casing shoe, to ensure it matches with the last drilling report. check your datum. Check that the drill floor elevation and the ground level, or whether for the seabed positions are correct. Then you need to check that the curves are on depth with each other. And this is where the tension curve, even though I won't be illustrating this, but the tension curve comes handy. So the tension curve can be used to identify possible zones where the tool became stuck, and usually to put some of the curves of depth, you have this fat lining where you just have the signature of the curve, just probably like a straight line with no indication. 4, this is important, check the caliper reading inside casing. And of course, you need to know what the casing ID is, and ensure that the reading it is reading the borehole size in the non-permeable zones which are not washed out. This is just for quality control. So the caliper reading is really very important. We want to ensure it's reading correctly in casing and also in the zones where they are quite competent and where you have no washout or no washout in those zones. Then the other important curve to check for talking about the integrity of the hole is the density borehole correction curve. It shouldn't exceed 0.02 gram per cc, except in clearly washed out zones. And usually when you have the density borehole correction curve really exceeding those values, going to 0.2 and larger values, you just discountenance interpretation at those intervals. For the sonic log, in the casing, the transit time should read 57.1 microseconds per foot. And also, you need to inspect the resistivity curves. I think in previous lectures, we've talked extensively on this. If all-base mod is being used, the shallow curves would usually read higher than the deep curves. That's except in highly gas or oil saturated zones. And likewise, if water-based mod is used, the shallow curves will read less than the deep curves. That's with the caveat. Usually that's for highly saline water-based mod. In theory, the curves should overlie each other in non-permeable zones, such as shales. However, some effects such as anisotropy and Schoenberg effects could cause that not to be the case, but usually in shales, the deep resistivity curve, the medium curve, and the shallow curve will usually overlie each other. And then you also need to look out for cycling type behavior of any of the curves, such as wave pattern. And this tends to be the case sometimes when you take logs while drilling. There's this corkscrew effect. Of course, this is just an indicator for possible tool malfunction. So these are just things that you take into cognizance before you go into the interpretation process. And what I have here, this actually should be, even though 0 to 50 is here, this actually should be 0 to 100, in some cases 0 to 150, so this is not cast in soft stone. 0 to 50 is not typical of arc line. It's more of 0 to 100, 0 to 150. That's for the gamma ray reading. Caliper, this is just indicative of the pipe ID and casing ID, as the case may be, an hole ID. And then resistivity is usually from 0.2 to 2,000 ohm meters, and is on the log scale. Density is usually the upper and the lower limit have about 1 gram per cc. You would see that there are times when it's not the case, and you see that in the example. For the Neutron log, it it's about 60 porosity units for the interval, minus 0.15 to 0.45, and then for the sonic log, 140 to 40. So, of course, one of the first things you need to do is to inspect the log header. And what you have on this slide is basically some things which would be most log data would have, and some of the header, some just before the log. So it's good for you to take note of this. In the next few slides, this is basically telling you what to expect. Of course, this is for somebody who hasn't been involved in well logging at all. The logs are usually displayed in tracks. So this is a track. In this case, this is track 1. The depth scale is usually not referred to as a separate track. And here, this is regular scale. Here, this is logarithmic, where you normally chart your resistivity. And here, this is a split scale, where you're having both logarithmic and linear. So these are standard log presentation formats. And here you would see that in this presentation, this is presentation for the SP. That's for the spontaneous potential log, caliper log, gamma ray. And so it says the typical thing, but note that what is presented here is typical log header presentations. It's not in any way general. So you have usually the SP and the gamma ray in some cases, and you've seen the example which I would, in my example in this video, it's the caliper and the density correction log that is presented first, and then you now have the SP and the gamma ray. And of course, the SP usually decreases to the left. So the rule given for finding clean sections is that the SP becomes less negative for increasing shear, and you see have it in one of the examples. The gamma ray curve is scaled in order of increasing activity. So deflections to the right indicating increasing shear content. So thus the gamma ray and the SP are shear indicators, and they are typical shear indicators. As for resistivity, which I've mentioned, which is usually presented, in this case, track 2 and 3. So usually the resistivity curve will have 3 measurements. So you have 3 resistivity traces. You have the deep reading, you would have a medium reading, and then you will have a shallow reading. And of course, if the deepest resistivity measurement should be indicative of true formation resistivity, that's in the case where invasion is not severe. The medium curve usually is an intermediate measurement and is highly influenced by invasion, while the third curve, which is the shallow reading, has a very shallow depth of investigation and reaches closest resistivity of the invaded zone. So by combining the 3 resistivity measurements, it's possible to compensate for invasion on the deep resistivity measurement. Of course, the induction dip has been used there, or could have been the lateral log, of course, depending on your mod system. The next track here. Now, the next track I'd like to talk on is the porosity track. Usually, we don't term it resistivity track or porosity track. It's usually track 1, 2, 3, but I'm talking about the track on which the porosity devices the log from the porosity devices are displayed. So usually porosity is expressed either as a decimal or in porosity units, and each porosity unit corresponds to 1%. So if you would look at, so for the topmost here, porosity here is expressed as a decimal. For this track, it's in percentage. And of course here, this is for the sonic. The porosity device measures interval transit time. So I mentioned in one of those scales you saw, the porosity was from minus 0.15 to 0.45, and that's for the neutron porosity. The middle example showed an additional density correction curve. I've mentioned that before. I think one thing that is important to note is that it's easy to show that the change in bulk density of 1 gram per centimeter cube in a water field formation corresponds to 60 porosity units. And I'll show you an example so that some of these things I'm talking about is brought home. So on this track, and this log display, this is actually from a log taken while drilling was on. You would see here towards the top that this is the density correction curve. This is the bulk density. First of all, this is in density units. And of course, you see the range is 1 gram per meter cube. And then for this one, so the way it's displayed, increasing density, increasing porosity to the left, and you see it in subsequent slides. And this is what I just mentioned, that the format is such that increasing porosity produces deflections to the left. So whether you are talking about the transit time, so for convenience, the way the contractor would display the porosity logs on the track would be in such a way that increasing porosity produces deflections to the left. I think one other thing which we need to be aware of is the matrix setting. So, of course, for this course, we'll take sandstone to be the matrix setting, but it's important to note that that is not always, in fact, it's not usually the case. So this setting corresponds to the rock type assumed in the conventional interpretation that establishes porosity from both the neutron and the density devices. The examples in L4, that's in this track. The matrix setting is listed as sandstone, and that means in that case, the rock type is sandstone. However, you should be careful, and if it's set to limestone, there will need to be some correction to take it to sandstone. So that's basically for our information. Now, having talking about or having given a few pointers to log quality control, let's now go into the quick look log interpretation process. And I'd like you to pay some good attention from here. So prior to detailed log interpretation, well site interpretation is undertaken. And this just implies that if you're working as a field engineer or a drilling engineer or well site supervisor, as soon as the logs are taken, you should be able to undertake some preliminary log interpretation. So it refers to rapid and somewhat cursory approach to scanning the available log measurements, and then the ability to identify zones and draw some conclusions about the zones of interest. These zones, which are hopefully hydrocarbon bearing, would warrant some closer and more quantitative analysis. And this is usually done in town, that's in the office. And of course, field-wide information from regional data, offset wells is usually brought to bear. So there are the three most important questions to be answered at the well site are: one, can porous clean formation be identified? Does the formation contain hydrocarbons? What is the formation porosity and saturation distribution? So these three questions will enable us to determine the quantity of hydrocarbons present, of course, if you are looking for the hydrocarbons in place. So formations with low shale content are more likely to produce hydrocarbon accumulation. So the first task is usually, that is after you have considered the log quality, is to identify zones with low shale fraction. These are usually referred to as clean zones. So this task is traditionally undertaken using the gamma ray and then the spontaneous potential logs. The qualitative behavior of the spontaneous potential log is usually to become less negative with increasing shale content. And for the SP log, as I've shown you earlier, it goes positive to the right. So as it goes less negative, as the SP reading trends left, that's indicative of decreasing shale content. So the gamma ray signal generally, with increasing magnitude, that is indicative of increasing shale content. For clastic reservoirs, that's basically our sandstone shale sequences. In nearly all cases, indication of reservoir rock will correspond to a fall in the gamma ray log. I think most of us should be aware of this by now, except for the occurrence of radioactive sands. And these are sands which have some high radioactive minerals. So anytime when you have these radioactive sands with radioactive minerals, other techniques need to come to bear. And one is the separation between the neutron and density measurements and NMR distribution, that's if it's available, and then some elemental spectroscopy analysis. What is displayed here is typical the SP presentation. So you'd see for this presentation on the right, you see that the SP, it increases, the SP reading increases to the right. As it increases to the right, that's indicative of increasing shale content, It trends to the left, that is decreasing shale content, and that is why you have this being identified as sandstone. Of course, it's not clean in this presentation. And then shale, so this is a shale sandstone sequence. And here, in blocky forms, this is the presentation with respect to the mud filtrate as compared to the connate water resistivity. So as mentioned earlier, clean sands, the sandstones, limestones, dolomites usually have low radioactivity. And some other formations like anhydrite, salt, lignite, coal also have low radioactivity. We see how they come into play. So ordinary shales have high radioactivity, we've talked about that, and that the Density sonic cross plot. Take note of this, that the density sonic cross plot may help distinguish between radioactive hot sands from shales. So a case where you're having the conflict, it's like you're having sands with radioactive minerals, the density sonic cross plot would come into play. What you have here is just how mnemonics for the gamma ray tool, typically what we'll be dealing with is API units, but it will be in ppm if you have elemental display on your plots. Earlier I showed the SP display, and this is for gamma ray. So for the reservoir rock types, they usually have very low gamma ray readings. Of course, we know the exception where you're having sandstones with radioactive minerals. And if this is what I said, I mentioned about the API scale for gamma rays. It is 0 to 100. In some cases, it gets as high as 200. So that's a matter of calibration. Now, probably the most reliable indicator for reservoir rock is the neutron density log. With the density moving to the left and the neutron either touching it or crossing to the right. And I will illustrate this in the example I have. Shales can be identified as zones where the density lies to the right of the neutron, typically by 6 or more neutron porosity units. The greater the crossover between the density and neutron logs, the better the quality of the reservoir. However, gas zones exhibit greater crossover for a given porosity as compared to log oil and water zones rather. So when you're going about to, in fact, in the first interpretation stage, step rather, is to establish what your volume of shale cutoff would be, and I would demonstrate this, so I won't spend much time here. So we've talked about identifying clean sand. So the next step would be, does that formation contain hydrocarbons? And once a porous clean formation is identified, the analyst is faced with deciding whether it contains hydrocarbons or not. So this analysis is done in an indirect way using the resistivity of the formation. Basically, if the porous formation rather contains conductive brine, the resistivity would be low. If it contains sizable non-conducting hydrocarbon, then the resistivity should be large. The hydrocarbons may be oil or gas. The distinction is most easily made by comparing the formation density and neutron porosity measurement. So yeah, we're coming to log presentation. So here, I brought this view graph up now because it talks about both lithology and fluid identification using density neutron logs. So the responses of the density and the neutron logs result in characteristic separations when plotted together. So the first thing is identification of shale zones. For shale, the density trends to the right and the neutron to the left. So let's see if we can identify a shale zone here. So this is a shale zone. So if you look at it, the density, that's with the red line, trends to the right, while the neutron porosity is on the left. So this is a typical shale zone. You see, there's a shale streak here. This is also, so let me highlight that. This is also a shale zone. This is a small shale streak here also. And this is really small. But the important thing to note here is for shale identification, and then you would also notice, because it's good for us to put it in context. See, relatively high gamma ray readings also here. And then the spike here and the spike here. So since the neutron responds to all hydrogen in the formation, this results to large porosity readings in shale sections. Note that said the porosity logs are presented in such a way that increasing porosity would be to the left. Now, that said, the next thing will now be sandstone. So for sandstone, to identify an interval with sandstone, the density would usually be to the left of the neutron. So you see, it's like a reversal of positions. You see here, the density is back on the left with the neutron on the right, and that's the same thing here, and all these zones, while the density is to the left of the neutron. Of course, when you have a very little separation, it's usually identified as water. When you have a larger separation, that's like within the same formation, within the same gas. And then when you have a much larger separation, and that is termed gas. So for this log, the convention used is red for gas, green for oil, blue for water. But it might be, some operators may use, contractors may use green for gas, red for oil. But it's important, and that's why it's important for you to take note of the header information before you go ahead with your interpretation. For limestone, similar to what the case for sandstone, the density is to the left of the neutron or just overlying it. Now, so we've looked at shale indicators, that's the spontaneous potential and the gamma ray, and then we've also seen how you can use the density neutron to identify for lithology identification, and also to some extent for fluid identification. So to at least have a working assumption regarding the fluids, start by comparing the density and the deepest reading resistivity log for any evidence of hydrocarbons. In the classic response, that's classic response, the resistivity and the density, also the gamma ray log, will tram line. That means they'll follow each other to the left or to the right in water sands, while in hydrocarbon, they will appear to be a mirror image of each other. To bring that point home, I'd like you to look at this view graph. So this is the case where you run the log in a water zone. So if you look at it, the gamma ray, the resistivity, and the porosity logs all trend. So the tram line, that's the term used, the tram line. If you look at the oil zone, you'll see that while the gamma ray and the porosity logs appear to trend each other, the resistivity is like a mirror image of the porosity plot or the gamma ray, depending on how you look at it. So here, it mays west, it's a may west thing. So this is just some typical signatures for discriminating between hydrocarbon sands and water sands. There are some exceptions to the rule though, and there are 5 of them which I have here. When the formation water salinity is very high, this could also lead to a drop in resistivity in clean sands. In shaly sand zones, having high proportion of conductive dispersed shales, resistivity may also fail to rise in reservoir zones. If the sands are thinly laminated between shales, the deep resistivity reading may be difficult to resolve. In fact, it may be impossible to resolve the sands and the resistivity will still be low in those zones. If the well has been drilled with a heavy overbalance, invasion may completely mask the hydrocarbon response when the formation water is fresh. This is also one very confusing situation. When the formation water is fresh water, in overbearing zones, the resistivity may be comparable to what you have in hydrocarbon zones, So those freshwater zones may present like hydrocarbon zones in some cases. It's because of their low brine content. Now, this is just presented. This is presented from effect. So, in this graph, in this log rather, we just have 2 tracks. So we have track 1, which in this case has the gamma ray, the SP, and the caliper log. And then in the second track, okay, this is the depth track. Remember, I said we don't usually consider this a separate track. And then here you have the resistivity. So you have the deep line resistivity, you have the medium measurement, and then you have a shallow measurement. So it's important that you see that there's some correlation between these 3 logs. That's the caliper, the gamma ray, and the SP. And then you could use them for some zonation. That's to demarcate the different zones. So you see from about 90 here, this is about 90 meters, to down to about 250, 255, thereabout. This is all sand. It's important to know also, you see that the caliper increases here. And here, there appears to be some washout. Now, if you look at this properly, so from, as I mentioned here, from 150 meters to 250 meters, you see that the resistivity, the deep resistivity measurement, the SP and the gamma ray tram line. And so we can identify this as a water zone. Contrary to that, just above it, that's between 90 and 150. And also, yes, also somewhere here, you see that the resistivity measurement has the Mill-West effect. It's like a mirror image to what you have here. So it doesn't trend with the gamma ray. So I think this is just another pointer to, so when either of the first 2 situations rise, that's the exceptions to the rule which I mentioned before. It's important to look at the absolute value of the deep resistivity curve rather than only the behavior compared to the density. As long as a known water sand has been penetrated, you can get a good idea of what the resistivity ought to be in the water-bearing sand. If the resistivity is higher than this value, whatever the shape, then hydrocarbon should be suspected. There is also an effect of porosity on resistivity. As porosity increases, the value of resistivity will decrease if water saturation remains constant. And we've also mentioned about the crossover, which is greater for gas zones. The measurement of RS code, this is the flushed zone resistivity, is used to get some idea of recoverability of hydrocarbons in the following way. If the value of the flush zone resistivity is found to be the same thing as the true formation resistivity, then most likely the original formation fluids are present in the flush zone, and that's indicative of the fact that no fluid displacement has taken place. However, if there's a marked difference between the flush zone resistivity and the true formation resistivity, then some invasion has taken place and fluids are movable. This can be taken a further step by considering the ratio of the flush zone resistivity to the true zone resistivity and comparing it to the resistivity of the mud filtrate to the resistivity of the formation water. Now, if the flush zone and the true formation resistivity, so if the ratio of this ratio is the same thing as the ratio of the mud filtrate to the resistivity of the water, then the flush zone and the non-flush zone have either the same quantity of hydrocarbons or none at all. Any hydrocarbons hydrocarbons are unlikely to be produced in this case. Any hydrocarbon, if the ratio of the flush zone resistivity to the true zone resistivity is less than, or it's not equal, if it's markedly different from the ratio of the mud filtrate to the ratio of the resistivity in the water zone, then some hydrocarbons have been displaced by draining fluid, and it's likely to be producible. Though I think I have an example which further illustrates this. One other thing that can be identified quickly are permeable beds. And for permeable beds, the SP is used, and also the multiple resistivity measurements. The presence of mud cake can be indicated by the caliper log. Note that the gamma ray does not give you any idea of permeability of permeable zones. Its own concern is about shale formation, lithology, and mineral composition. So if you look at the profile in W3, that's here, I'll come there. The three resistivity curves fit well in the non-permeable bed. So if you look at it here, that's from the beginning of this log down to this portion, the three curves tend to overlie each other. In the sandstone, the microlateral log, which is controlled by the flush zone resistivity, shows a low resistivity compared to the deep and the shallow resistivity log. And this is an indication to permeability. It's an indication to some degree of invasion or displacement of the fluids in the vicinity of the well bore. And this is also shown here. So you see, this is definitely shale. You see that the resistivity curves overlie, but here where you're having good separation, so this is permeable zone indicated by the resistivity separation, and of course, in this case, the SP log. So separation of the resistivity logs results in an invasion effect and indicates permeable zones. That's for, and of course, where the three curves fit or overlap each other, that's indicative of a non-permeable zone, really shale. So this just summarizes quick look interpretation. So you see, this is just a summary. You can make reference to this just as a guide. Always, but know that there are always exceptions to the rule, but this is typical. And this is the point I was trying to emphasize. When your flush zone, the resistivity within your flush zone is equal to or equivalent to the resistivity in the true formation where you have little or no invasion, little or no, yeah, that's just indicative of the fact that the drilling fluids, the original fluids there have not been displaced, and that's an indication to no invasion. And also, if RMF is equal to RW, that's the mud filtrate is equal to resistivity of the formation water, then we'll say that there is no movable hydrocarbon. And of course, if definitely these ratios are not equal, then you see that some of the original wellbore fluids have been moved due to your drilling activity. Now, that said, this is the step, or no, sorry, these are the steps which we'll be using for quick look interpretation. One is to evaluate lithology, determine the net sands from gamma ray and the density neutron. Two, identify the zone with water. That's 2A. 2B is to define contacts. 3 is to calculate porosity from radio density neutron or sonic. There's usually a preference for the use of the density log. Next would be to calculate the resistivity in the water zone, and then to get water saturation. And then a fifth step is mentioned to recognize minerals, or at times what you might call odd formations, via your logs. So to elaborate on these steps, for the very first step, that's identifying the clean zones, we use the gamma ray log typically, and here it says choose a cutoff to differentiate shale from sand. And typically a cutoff of 50% is used. I'll show you how that is done. You draw a line in the gamma ray track at this value. It's not illustrated here, but I have it there. You shade the line between, the line and the gamma ray curve to delineate potential sand. And you see here which is shaded. So this is the cutoff. The whole idea is anything that falls outside this line. So you see this gamma ray, this portion is higher than this line. So this is taken as shale, and the same thing here. So all those points to the right of the shale cutoff line are regarded as non-reservoir rock, and this is reservoir rock, and this is complemented by using the neutron density. And remember what we said, for sandstone, your neutron trends to the right of your density curve. Remember that in shales, the neutron porosity measurement is usually high, and that's because of the high hydrocarbon content. So the next thing is to try to identify, is for fluid type identification and contacts, basically. So it says examine the resistivity logs, note change from high resistivity to low resistivity in net sand. Of course, high resistivity tends to be indicative of hydrocarbon, but it's not always the case, and vice versa. So you see here they're illustrating the use of the separation to recognize the water zone from the oil zone and then from the gas zone. In this case, you see this is where at this depth that's about 5,069 thereabout. And that's where this should have been the contact. But because this fell in non-reservoir rock, what you can probably just do here is to know where you're getting your gas down to. And then where you're getting your oil up to, gas down to, and this is oil up to, and this is water up to. So the next step is to calculate porosity, and it's a function of the porosity logs which are run on the field. So if logging a number of runs, you may have only sonic porosity initially, even though that's usually not the case now. Assume the matrix transit time for the lithology drilled and then the transit time in mud, for the mud filtrate. Refine your porosity calculation with the neutron density data. It's not efficient having one run. So typically it's a combo done. So since it's typical to have at least two porosity measurements or two porosity logs, you can estimate the porosity from the neutron density by drawing a line halfway between the two curves and reading off the neutron scale in oil and water legs. And estimate the porosity of the gas leg by plotting sample data points from the log on the chart book of the neutron density plot. And this shows you where the contractor's chart book comes into play. And the next thing would be to now calculate the resistivity of the water zone, water resistivity. So you read the deep resistivity measurement in the water leg, and then you, on the assumption that it's a clean sand, the Archie's equation applies. Note that the Archie's equation only applies for clean sand. And then if, of course, in the water zone, you expect the water saturation to be unity. So if water saturation is unity, then it becomes, that's the Archie's formula. Of course, note that in this case, both M and N are assumed to be 2. So that is 1 over the square of porosity times the ratio of the formation water resistivity over the true formation resistivity. And therefore, you can now calculate for the formation water resistivity by multiplying the true formation resistivity by the square of the porosity. And the next thing is to recognize what are called odd formations. In this case, it's referred to as minerals. And what you see, there are times when you could have certain, so in this case, to identify calcite, for instance, to get calcite stringers, in this particular log, you had some calcite in the formation. And if you look at this, so this is where you have the density neutron log here. Even the density neutron, this is actually a sonic log presentation. So if you notice, both the density and the neutron logs trend to the right, indicative of low porosity. Resistivity is high, and the gamma ray is low. And also the sonic transit time is low. So this is, interestingly, this is not indicative of hydrocarbons, but rather of calcite. Calculated porosity is very low, and these intervals should be excluded from the net reservoir. So if you are doing your evaluation, this portion should be excluded from your net sand. This one refers to the identifying coals. That's the presence of coal. In this case, here, both the density and the neutron porosity trend to the left, and that's having very high values. Resistivity is also high, and then the gamma ray is low. So they are recognized as coals because the neutron and density indicate unrealistically high porosities. Sonic, also the interval transit time is quite high, and then the hole is washed out. So it's friable. These intervals should be flagged up as non-net reservoir. Porosity set to 0. So this just identifies certain formations which could show up within your interval of interest, but they should be counted as non-reservoir rock.